Hey, Apply 30. Guess where I am? It looks like we are back at school. Well, I am anyways. For your sake, things don't change too much. You should still expect some videos to come in on a regular basis. Probably a little bit more frequently because I have access to the school facilities now, so I can upload on a more regular basis. Without further ado, our next topic is something called optimization problems. So that's when we're trying to identify what the greatest or the maximum or the minimum data points would be for some sort of inequality. To understand optimization, we're going to work through a couple of word problems. This first one is going to go to a certain point and then we're not going to be able to solve it any further. But then the next example we look at, we can get a significant amount of information from it. Okay, so looking at this example, we've got three teams that are traveling to some sort of tournament. If you're following along in your book, it's on page 325, and it's a basketball example. So in this case, we have three teams that are going to a tournament. They're either going in cars or in minivans. Cars, not the first point here, cars can take 4 team members. Minivans can take 6. Each team has no more than 2 coaches and 14 players. So a maximum a team could have is 16 members, 2 coaches, 14 players. You could also have 15 if you had 1 coach and 14 players. I suppose you could have less, right? It says no more than 2 coaches and 14 players. So maybe you have 10 players and 1 coach. So there is a parameter, there's a limitation on the maximum number of people for a team, but we don't know what the minimum is. Not at this point anyways. What we need to do is determine the combination of the minimum and maximum number of vehicles. So it's a tricky question, but we realize that there's inequalities that are at play here. What you've worked on previously is determining what those inequalities were, and you would state them and then you would graph them. We're going to do the exact same thing. We got to figure out what the inequalities are first, and each of them shows up with each of our points. So let's label what those inequalities are. So we can identify our inequalities. You'll see there's 3 of them. There's 2 at the bottom and there's 1 up here. I'll tell you about those in just a moment. Recognize though that we have to state our parameters first. So what is our solution set going to look like? I'm going to say that X represents my cars. You could use C. You could use M for minivans. I'm using X for cars, Y for minivans, simply because that's what I'm comfortable with on Desmos. If you're comfortable in a different way, that's totally fair game as well. So if X represents cars, I have to state that X must be an element of whole numbers. Y, if that represents my minivans, Y must also be an element of whole numbers. Remember, whole numbers are 0 and any positive nice number that follows. Can't use any negative values, so no integers, because you couldn't have a negative of a car or a negative of a minivan. Can't use rational or irrational numbers, right? Because you can't have a decimal of a car or a fraction of a minivan. So we're going to say that X and Y are both elements of whole numbers. Then we can state our inequalities. So I'm actually going to go backwards, start at the bottom, because I have the 2 basic ones here. X, which is our cars, we can have up to 12 of them, so we have a maximum. So X must be less than or equal to 12. We could take all 12 cars, or we could take less than that. We have 4 minivans available. That means that we could take all of them. Y is less than or equal to 4, or we could take less than those 4 minivans. Both of those are options. Our last inequality is up in red here, and that is 4x plus 6y is less than or equal to 48. And that's representing how many people are going on this trip or going to the tournament. We know that each team has no more than 2 coaches and 14 players. So at most, each team could have 2 coaches and 14 players, 16 people in total. If all 3 of our teams have 16 people, that's where this 48 comes from, because 16 times 3 is 48. It's possible that we have less. As we stated before, we could have 1 coach and 10 players. But that's what this less than or equals design will account for. These red inequalities, we call those constraints. Okay, they're limiting where our data falls in between, and that helps us identify and optimize our problem. And you might have noticed the blue bracket I had in the middle as well. We had an additional point that we didn't account for. This is what we call our objective function. It's what we're actually looking for when we're trying to optimize, and that's how many vehicles we have. So I've chosen a new variable for that. I've chosen capital V. You can use any letter you want. That capital V is equal to X plus Y. The number of cars plus the number of minivans will tell us how many vehicles we have in total. The objective function is typically what you're trying to solve. Oh, and pardon me, but I made an error on this inequality here. I've just swapped the X and the Y positions, just in the way that I've written it down. compound. That's why it helps to use, say, C for cars and M for minivans. But I've made that correction now. It should be 4y, that's how many minivans you have, plus 6x is less than or equal to 48.